Imagine turning on your computer one day and realizing that the rules you've lived with for years have quietly changed overnight. No flashy marketing campaign, no dramatic keynote, no pop-up telling you this is the future. Just Linux doing what Linux always does, evolving steadily, methodically, and then suddenly reaching a point where everything feels different. That's exactly what has happened now. Linux has just gained a feature that doesn't merely improve performance or polish the desktop, but fundamentally reshapes how we think about operating systems, how software is built, how hardware is used, and how control shifts back into the hands of users in a way we haven't seen before. For decades, operating systems have followed a familiar pattern. They manage hardware, schedule tasks, isolate programs, and provide a layer for applications to run on. Linux excelled at this from the start, especially on servers, supercomputers, and embedded devices. On the desktop, it steadily matured, becoming more user-friendly, more beautiful, and more powerful. Yet beneath all of that progress, one assumption remained mostly untouched. The operating system is something static that you install, update, and hope never breaks. Configuration drift, dependency conflicts, broken upgrades, and mysterious bugs have been accepted as the cost of doing computing. Linux users tolerated this better than most, but it was still there, lurking in the background. Now that assumption is finally cracking. Linux has crossed a threshold where the operating system is no longer just a mutable pile of files that slowly degrades over time. Instead, it is becoming something closer to a living system with memory, reproducibility, and self-awareness. The feature that enables this shift is the deep, system-wide integration of immutable, atomic, and declarative system design directly into mainstream Linux workflows, not as a niche experiment, not as a research project, but as a practical, everyday capability that anyone can use. At first glance, the idea seems simple. Instead of changing the operating system piece by piece, Linux can now update, roll back, and reproduce itself as a complete, coherent state. The system knows exactly what it is, how it was built, and how to return to a previous version if something goes wrong. But the implications of this simplicity are enormous. It changes how we update systems, how we secure them, how developers ship software, and how users interact with their machines. Think about updates. Traditionally, updating a Linux system means replacing thousands of files while the system is running. If something fails halfway through, you're left with a half-updated system. If a dependency changes unexpectedly, an application might stop working. If a configuration file gets overwritten, subtle bugs appear weeks later. With the new approach, updates are atomic. Either the new system boots and works, or it doesn't. If it doesn't, you reboot and you're instantly back to the previous working state. No repair sessions. No frantic searching through logs. No reinstalling the OS because an update went wrong. This alone would be revolutionary, but Linux doesn't stop there. Because the system is described declaratively, you no longer think in terms of what commands did I run to get here? Instead, you think in terms of what do I want my system to be? You define the desired state, and Linux ensures that state exists. This flips the entire mental model of system administration. The operating system becomes something you describe, not something you constantly patch and tweak by hand. Now imagine what this means for developers. Setting up a development environment has always been painful. Different library versions, conflicting dependencies, tools that work on one machine but not another. Entire careers have been built around solving these problems. With this new Linux capability, a development environment can be defined as precisely as the operating system itself. A project can specify exactly which compiler, which libraries, and which tools it needs. Anyone, anywhere, can reproduce that environment perfectly. The phrase "works on my machine" begins to lose its meaning. This reproducibility also extends to time. You can rebuild the same system months or years later and get identical results. That is a profound shift. It means research can be replicated more reliably. It means old projects can be revived without archaeology. It means long-term maintenance becomes more realistic and less fragile. Security is transformed as well. An immutable system dramatically reduces the attack surface. Malware that relies on modifying system files suddenly finds itself blocked. Even if something malicious runs, it disappears on reboot. Combined with strong sandboxing and modern kernel security features, Linux starts to look less like a traditional OS and more like a hardened platform designed for a hostile world. Updates become safer because they are tested as complete units. Rollbacks are instant. Auditing becomes easier because the system state is explicit and verifiable. For enterprises, this is a game changer. Managing fleets of machines has always been expensive and error-prone. Configuration drift means that no two systems are ever quite the same. With declarative atomic Linux systems, every machine can be identical by design. If a machine misbehaves, you don't debug it for hours. You simply redeploy the known good state. Infrastructure starts to behave more like code and operations become more predictable. On the desktop, the impact is subtler but just as important. Users gain confidence. You can experiment without fear. Try a new driver, a new kernel, or a new desktop environment, knowing that you can always go back. The operating system becomes a playground again, not a fragile artifact you're afraid to touch. This spirit of exploration is deeply aligned with what Linux has always represented, but now it's backed by powerful safeguards. What makes this moment truly significant is that these ideas are no longer confined to a single experimental distribution or an academic discussion. They are influencing the broader Linux ecosystem. Package formats, update mechanisms, and system tools are adapting to this new reality. The kernel itself continues to gain features that support isolation, immutability, and reproducibility. Hardware vendors are starting to take notice because a system that can reliably update and recover is a system that generates fewer support calls and happier users. There's also a philosophical shift happening here. For years, proprietary operating systems have marketed simplicity and reliability as their selling points, often at the cost of user control and transparency. Linux is now showing that you don't have to make that trade-off. You can have a system that is both deeply understandable and remarkably robust. You can see how it's built, change it to your liking, and still enjoy the safety net of atomic updates and rollbacks. This feature also blurs the line between desktop, server, and cloud. The same principles apply everywhere. Your laptop, your home server, your cloud instances, and even your containers can all be built from the same declarative foundation. Knowledge transfers more easily. Skills scale better. Linux becomes not just an operating system, but a unified platform for computing at every level. Some people will say this is too complex, that it introduces new abstractions to learn. And they're not wrong. There is a learning curve. But it's a different kind of complexity. Instead of wrestling with unpredictable behavior, you invest effort upfront to gain long-term clarity and control. It's the difference between constantly fixing leaks and redesigning the plumbing so leaks are rare in the first place. History shows that shifts like this take time to be fully appreciated. When package managers first appeared, many people resisted them. When virtualization became mainstream, it seemed unnecessary to some. Containers were once dismissed as a niche tool. In each case, Linux quietly absorbed the innovation, refined it, and eventually made it indispensable. This new feature follows the same pattern, but its reach is broader. It touches every aspect of the system. As more users adopt it, expectations will change. People will begin to demand safe rollbacks, reproducible systems, and declarative configuration as standard features. Distributions that don't offer these capabilities will feel increasingly dated. The definition of what a modern operating system is will shift, and Linux will be setting that definition, not following it. What's especially remarkable is how this aligns with Linux's original values. Transparency, control, collaboration, and resilience. This feature doesn't betray those values. It amplifies them. It takes ideas that were once available only to experts and makes them accessible, practical, and useful in everyday computing. So when we say Linux just got a feature that changes everything, this isn't hype. It's a recognition that a long-running evolution has reached a tipping point. The operating system is no longer just a foundation you build on top of. It's becoming a carefully defined, reproducible artifact that you can trust, share, and evolve with confidence. Years from now, we may look back at this moment the same way we look back at the introduction of multitasking, networking, or virtualization, as a quiet change that, in retrospect, reshaped the entire landscape. And as usual, Linux didn't announce it with fireworks. It just shipped the code, let people use it, and changed everything anyway.